In this lecture, we're going to talk about subtyping. This is related to the notion of subclassing, which came up in the lecture on safety that we had earlier. There we looked at this simple little three-class hierarchy. I have a class A, say an animal, and then two extending classes, bird and cat. And what we noticed in that lecture is that it's always safe to treat a bird like an animal. But the reverse is not, in general, safe. I can have an animal and attempt to treat it like a bird, but in fact, someone, instead of giving me a bird, might give me a cat, like is happening on line 12 here. And if I get a cat and try to treat it like a bird, well, things aren't going to work great for me. In Java, I'm going to get a class cast exception. That's subclassing, where we have a downcast or an upcast from one class to another. Subtyping is similar. It's about the idea that I can use one type where another type is expected. And so with these animals and birds, I can take a bird value and assign it into an animal variable, and that's fine. And it's not just direct assignment. I can also have this happen through method calls. If a method is consuming animals, it'll be perfectly happy to get a bird. And if I have a factory that's producing birds, well, I certainly could use that factory to give myself an animal. When we talk about this kind of substitutivity, we call it subtyping. It's safe to use an instance of B where an A is expected. And that's because if you think of these as sets, well, B is actually a subset of A. Every bird is an animal. When we're thinking about values of a given type, we call this subset relation subtyping. In these examples, subclassing and subtyping coincide. When two sets are related by a subset relation, we note it this way. The corresponding notion of subtype is written like this with a less than sign and a colon. It just corresponds to this subset notation. We can use subtyping to make deductions about sets. So if we know that Y is an element of B, it's a bird, and every bird is an animal, that's a subset, then we know that Y is an animal. The corresponding deduction is written in type systems as follows. So if Y is a B and B is a subtype of A, then Y is an A. This is just formalizing the idea of an upcast. But we'll see that subtyping is not just subclassing. We also need to deal with parametric types, as we've discussed in a previous lecture. Like the subset relation, the subtyping relation has some nice mathematical properties. In particular, it's a partial order. We don't need to know a lot about partial orders, but it's good to know two things. One is that partial orders are reflexive, and therefore every type is a subtype of itself. In addition, partial orders are transitive. So for example, if a canary is a bird, and every bird is an animal, then canaries are animals. This corresponds to the intuitive idea of one set being within another, which is obviously a transitive property. There are also other properties that we may have for a type system. One of them is that we might have a top element. This is an element that's greater than all other types in the language. In Java, this corresponds to java.lang.object. That's above all of the object types. There is actually no absolute top type in Java because the base types and the object types are unrelated, and there's actually no top type for base types either, like ints and floats. There's no type that joins those. But there is for the object world. In Scala, we have any, which is above all types, and any ref, which is just above the reference types. So any ref corresponds to object. You can see these types show up when you mix elements of a linked list. Scala's type inference system is always trying to infer the best type it can find. And so if you have a list with hello and some other object, well, the best it can do is to come up with any ref. If you have a list with hello and some base type, well, then the best it can do is just any. If we can have something on the top, well, why can't we have something on the bottom? This is actually unusual because if you think about it, the top type is corresponding to the universal set. It includes every possible thing. A bottom type instead is empty. There's nothing there. And most languages don't find a use for this type. It's less than all other types. Therefore, it must be the most specific of everything. It's like the thing that is both a cat and a dog. What is the thing that is both a cat and a dog? It is nothing. In Scala, there is such a type, and in fact, it's called nothing. There it is, sitting down at the bottom. It's below null, which is a bottom type for object types. Nothing means really nothing. It's not even null. What good is this bottom type in Scala? Well, it allows us to express properties of empty things. Like, for example, what is the type of an element inside of an empty list? If you try to give any actual type, then you're going to end up in trouble because any specific type will be too specific. What's inside the empty list? Well, nothing. What's nice about this is, as we'll see, this allows us to infer that a list of nothing is actually a list of anything. So if you have an empty box, can't you just say it's a box of anything? I've got a box of angels, and there's nothing in it. I've got a box of alligators, but I just don't have any alligators right now. I've got a box of unicorns, but there just don't happen to be any. Thinking about boxes of nothing may seem a bit esoteric, but this turns out to be very useful in practice. Imagine we have nil, and we are trying to represent that as some kind of list. Well, no matter what I pick, I'm going to get it wrong sometime. Suppose I try to say that nil is a list of integers. Well, then if I prepend a string, I've got now a string and a list of integers. The best type I can do to combine those is any. That's not a very good type. It makes no sense though, because nil actually doesn't have an integer. It's just empty. So this type is just constraining me for no good reason. That's what nothing does. Nothing says, well, nothing is nothing. And therefore, a list of nothing could be a list of anything. In particular, it could be a list of strings. And therefore, when I put a string in front of a list of nothing, I can get a list of strings. What we're seeing here is a property of Scala lists. That is, because nothing is below everything, it's a bottom type, a list of nothing is below a list of anything. Let's look at the example where we have animals and birds. I'll give the animals the method f and override that in the bird class, and then we'll have the birds have their own method g. Note that if I mix animals and birds in a single list, then the type that Scala will infer is a list of animals. It's not a list of birds because there are some more abstract things in there. But if I have all birds, well, then Scala will say that's a list of birds. These are both fine. And this top line works because of subclassing, because every bird is an animal. It's okay to think of the birds as animals in this list. But can I take a list of birds and treat it like a list of animals? Is that safe? Well, it's okay, because what can I do with the animals? The only thing I can do with the animals is invoke f. And in fact, all the birds are going to have an f. It's an overridden f, different f, but it's still an f. And so this is fine. Every bird is an animal. Therefore, when I access the list, I'm getting out birds. Those are animals. It's all fine. We say that the list operator is covariant. That means that if B is a subtype of A, then list of B is a subtype of list of A. In general, we'll say that a type constructor T is covariant if whenever B is a subtype of A, we know that T of B is also a subtype of T of A. There's lots of covariant constructors in Scala. Another one is the tuple constructor. So if I have a pair of a dog and a bird, I can treat that like a pair of animals. That's perfectly fine. What tuples and lists share in Scala is immutability. What about mutable structures like arrays? Well, we can initialize arrays just as we did before. So I can take an animal and a bird and put them together and get an array of animals. Likewise, a couple of birds will give me an array of birds. No problems there. But what about taking the array of birds and treating it like an array of animals? This turns out to be not safe in Scala. I'll get an error in the compiler saying what I wanted on the left-hand side here was an array of animals, but you gave me an array of birds, and that's not going to work out here. And it says, note, B is a subtype of A, but class array is invariant in type T. You may wish to investigate a wildcard type. What's going on here? Why are they being such a nanny state language? Well, the problem with mutable arrays being covariant is you can have executions like this. I take the array of birds, treat it like an array of animals for a little bit. Now, in the 0th index, I can just add an animal. Note that this is not a bird, and so it doesn't have, in particular, the G method. But since I've aliased this array between both bird and animal types, I can actually still access it via the bird reference and invoke method G. This is unsafe access if it's allowed. So Scala is a safe language. It's got to stop this somehow. And it actually stops it on the first line here. We stop the assignment of B's into A's. In general, covariance is only safe for a read-only structure. That's an immutable structure. It actually doesn't need to be immutable per se. We just have to have a read-only view, meaning we cannot write into this structure. We usually think of read-only things as being immutable. That's certainly an important case. But read-only is actually more general. I might have, for example, two ends of a network socket. The one end that I'm reading from, if I don't write into that socket, it's just a read-only socket, then that is read-only, even though it's a mutable structure. But if we go back to the error message, Scala told us to investigate wildcard types. So maybe we should do that. Here's the expression of A as a wildcard. This says that A's holds not an array of animals, but an array of some specific subset of animals. We don't know which subset. It could be birds, it could be dogs, no idea, but some subset of animals. What does that mean? It means that, well, we can do the assignment now, so Scala will pass this assignment. We can treat that array like an array of animals. However, when we try to put something in it, we'll get an error. What's the error going to say? Well, it says, I found a mismatch. You gave me an A, but I want $1, where $1 is some specific kind of animal. And note that I don't have a way to create a $1 thing. I don't even know what it is. In fact, no one knows what it is, and that's why you can't create it. Now, you can read out of this just fine. You can read the animals, but you can't put them in because nobody knows exactly which kind of animal it is. This is what's called a wildcard. It's like, I'm not sure what it is. I know it's something, but I'm not sure what. And that means that you can't actually add things in safely. You can only get them out. So effectively, we created a read-only structure here. There's no way to write into an array of this type. If we can have a wildcard that's a subtype of some type, it's interesting to ask whether we can also ask if that wildcard might be a supertype. And indeed, we can. Here's an example of this, where B's is no longer an array of birds. It's an array of something bigger than birds. It might be animals, but it might also be things that can fly, including airplanes and stuff like that. Now the relationship between A's and B's is reversed. I can safely take an array of animals and treat it as an array of something that's a superset of birds. So here, animals happens to be one of the things that's a superset of birds. There's also flying things, but animals is one of them. And so this is sound. It's okay to actually put a bird into this array of animals because a bird is an animal and this is all going to work out. However, when I try to invoke a method, I'm going to get in trouble here if I try to invoke a method of the bird class on this array. And why is that? Well, because it may actually contain non-birds. We might have other things in there, like dogs. And therefore, this is going to give us a type error. The type error is interesting. Look, what it says is that G is not a member of $1. Well, what's $1? $1 is the bigger set, the set that includes birds, that I don't know what it is. It's maybe animals, it's maybe flying things, it's something. What we've got here is a different kind of variance. Note here that every bird is an animal, but here these things are varying the other way. We're taking an array of animals and treating it as an array of things that are a superset of birds. So this is contravariance. The variance goes the other way. This is sound for write-only structures. But here we actually do have a structure we can read. So how does Scala deal with this? It's going to degrade the type of the structure. It could have different kinds of flying things, or it could have different kinds of animals. I don't know which one it has. And therefore, the only safe thing to access out of this is going to be any. Any is safe for any type, because no matter what's in this array, it's going to be a member of anything. And what I can do, if I want to use it in a specific context, is to actually do a downcast, which will be checked, and then I can recover the information about the type. Okay, well, that's all super interesting, but let's go back and review. Scala lists, just the basic stuff. Scala lists are covariant. What does that mean? Anytime I have a class, bird, which is a subset of animal, then a list of birds can be treated as a subset of a list of animals. That's covariance. Scala arrays are invariant. That means you cannot take an array of one type and assign it to a variable that has an array of a different type associated with it. Why? In order to stop the read-write problems that you can see here. We can both read and write, and therefore it's not safe to do this kind of downgrading or upgrading of the type. It's just not safe. You can see the two aspects of this with wildcards. We can either forget about what's going into the array, and therefore we can't write it anymore, or we can forget about what's coming out of the array. So when we actually access it, we just get it at top type. Not every language makes the same choices. In Java, arrays are covariant. Therefore, this program actually type checks and can run. So here I'm going to create an array of birds and associate that with a reference that expects an array of animals. So I can now, through my array of animal reference, insert an animal, then try to get that out through my bird reference as a bird, then try to invoke the G method. Remember, G is defined on bird, but not on A, and therefore this would be an unsafe access. This is something we cannot allow to happen in the language. So recall that Scala will stop this on line 4, simply because arrays are invariant. You're not allowed to take an array of birds and treat it like an array of animals. Recall that with Scala wildcards in array B, I could actually get to line 6 before the compiler threw me out. But Java will accept both lines 4 and line 6. It accepts the whole darn program. What it does instead is give a dynamic error on line 5. When I try to assign the A object into the array of B's, Java detects this at runtime because it knows the type of arrays. It sees that the wrong kind of thing is being assigned, and it throws an array store exception saying, oh, you're trying to put an A in here? No way, buddy. This is an array of birds. We're not taking some abstract animal. In order to maintain the safety of the language, this check is required. I mean, either we have to check things going into arrays or we have to check them going out. We have to check them somewhere if we're going to compile this program. And I guess the idea here is that you assign to arrays slightly less than you read from them. And so they check them at the point that the write happens. So note that we have to pick something here. Either we make arrays invariant like Scala, or we have to check things like this in Java, or we simply throw out safety like we do in C. But we've got to do something if we want to maintain safety. Why would they do this in Java? Why would they accept this expense? It seems extraordinary. And it is extraordinary unless you go back in time. In 1995, Java didn't have parametric types at all. So if you wanted to, for example, sort a bunch of things, what would you do? Of course, I don't want a sorting method that's specific to strings. I'd like to have one that's generic for any kind of comparable type. And so we'd like sort to be generic at some high type. But in order to pass a string array into a method that expects an array of objects, we need covariance. And that's why it's there. Of course, in Java, after 2005, we can do this better. And they did do it better. The sort method changed. This is actually the type of the sort method that you'll see in the Java APIs. The type is a little bit hard to read. It's, I think, easier to read in Scala. Same thing, but just written in Scala. So the sort method takes a parameter x, which is a type, and an array of x, and then it sorts it. Okay. We have a bound, however, on x, which is that x must be a comparable type. And what do we need to be able to compare to? Well, we need to be able to compare at some type that includes x. Now, this may seem a little bit bizarre, but it actually makes sense. If you have a class A that is comparable to A's, and I have some class B that extends A, but doesn't change the comparable method, well, then I'm in this situation where I may have an array of B's and sort them. And what I'm going to do is sort them using the comparison operation at type A, not at type B. And that's why the comparison operation here is constrained to be at some supertype of X. We don't actually care which one. We just need to have some way to compare them. In order to really talk about invariance, covariance, and contravariance, it's useful to have 3 types and not 2. So I'm going to extend our animal bird metaphor to include a specific kind of bird. Let's call them canaries. Every canary is a bird, is an animal. Now we're going to define 3 types. A source is something that allows you to get something. That's a covariant object because I can always get more abstract things out safely. A sink is a contravariant object because I can always put in more concrete things. A reference here is an invariant object because it's both a source and a sink, and therefore I can both get and put, and therefore I don't have any safe variance that I can do. Let's look at our example with a reference for birds. We can treat that reference for birds as both a source of animals and a sink for canaries. That means that I can create a canary and put it into this reference for birds. That's safe. Note that the reference still just holds birds. We're good. Then I can get things out and look at them. I can look at them either using ref.get or source.get. And what I get is actually 2 different types. So you can see my canary object is at hash as written here. And when I get the object out here, I actually do get the same object. But note that I get it at 3 different types. It was created as a canary. When I use the reference to get it out, I actually get a bird. And when I use the source to get it out, I get an animal. So you can see contravariance and covariance in action. Contravariance allows me to put the canary into this ref using a sink. Covariance allows me to get the object out of the ref at a higher type using a source. Note that I can't use the source to put and I can't use the sink to get. And that's crucial to all of this being safe. A similar thing happens with functions. So I can have a producer or a factory which, when given nothing, gives me back a y. This is safely covariant because I can always think of the thing I'm getting out as being more and more abstract. Likewise, a consumer or a sink is a function that takes something and gives me nothing. It's just so needy. And there it's actually safe to be contravariant because if the function wants a bird, I can give it canaries and that's okay. A function in general has both of these aspects. It both consumes x and produces y. So it will be contravariant in its parameter and covariant in its return type. This is in contrast to a function that both takes and returns x. In that case, we must require the function to be invariant. The plus and minus symbols written here are called variance annotations. We use plus for covariance, minus for contravariance, and simply nothing for invariance. And these variance annotations are checked by the Scala compiler. If you get them wrong, the compiler will complain. It'll say, I'm sorry, the contravariant type y appears in covariant position. So it has some notion of what's correct for functions and references and everything else in the language, and it won't let you get it wrong. The same thing happens if you try to make the consumer covariant. It simply won't work. The compiler will complain. So let's suppose that we have some type B that's a subtype of A, and we have some type constructor T that takes a type parameter. Then we can say that when T of B is a subtype of T of A, the type constructor T is covariant. And when we have the reverse, the type constructor T is contravariant. And when we have neither of these, the type constructor is invariant. We have some examples. So an example of a covariant type constructor is list. An example of an invariant type constructor is array. I don't actually have a good collection example for a contravariant type constructor because a collection that you can never read from is just not very useful. But that's the example. It's a write-only collection. In distributed systems, we have these things where you can write into a collection from one thread and only read it from another. So that would be an example of a contravariant thing. But I don't have a good example among the things we've talked about. Looking at our reference examples, we said that the read-only source was covariant, the write-only sync is contravariant, and the read-write reference is invariant. And with functions, the producing function that gives us x's is covariant. The consumer function that just eats x's is contravariant. And the operator which takes an x and gives me back an x is going to be invariant. We've seen two kinds of polymorphism in statically typed programming languages. There's parametric polymorphism, where a type has a parameter, and subtype polymorphism, where we can use a more specific type where a general one is expected. So a subset where the superset is expected, the bird where the animal is expected. We've seen just a tiny bit of the rich world of type theory. There's a lot more to look at. We saw a little bit about bounded polymorphism here. For example, in our sorting method, we had a bound on the parameter that it must be comparable. We also looked a little bit at the kind of use site variance and wildcarding that Scala and Java have. But there's a whole lot more to learn. If you find this material interesting, you should continue to check out Scala. And maybe also look into TypeScript. This is a typed form of JavaScript that has a fascinating type system.